right? So today, based on this my perception that how it is proceeding, so I am thinking to start with some two basic programming. So first part of this programming is this one on deep neural network. So can you see this slide and you can follow it? You can read the line text here.
Yes,
Yes, sir.
My cursor is also visible, no?
correct.
Okay, good. So we'll start with this one. So probably till now you have not used that much in Google Colab. Have you used Google Colab already?
Sir, we are aware of that, but I mean,
Okay, today you will use that one. So first thing is that I am sharing this link. This is in my Google Colab. How can I share? So basically the chat box I am sharing. So you try to open with your Google ID. Means so in your computer, if it is logged in with your Google ID, you can open it. And then you can try to save it as your Google Colab. Means in your Google Colab folder will be created where this same programming you can save actually. And then you can run along with me. So tell me how many of you is successful with this.
successful. Sir. It's opening.
Okay. Second thing, do this one. If you open this, then you will see that another link is just below it. And it is the link where you will find most of the information about this part of this programming what we will discuss today. So this is my more step-by-step discussion. So mostly that exactly same thing we'll do. Step by step we will follow this one. Okay. So if it is not already there in your Google document, you create it will automatically create one folder like here you see the Colab network. Similarly, it will be created where your file will be there. So first try that thing. Second thing is that in the browser open this link. So what I cannot understand that whether you are successful in doing so. If anybody has problem, is there any way raise your hand or something you are facing problem, or you can unmute and you can tell that you are facing problem. So since nobody is talking, should I believe that everybody could do that? Okay. Okay, I got okay. Okay, good. Okay, so now we will go step by step. So already you have enough exposure already in the deep neural network. So here, what are the steps we are doing? So here it is written that you will explore and process data, and this is very simple data basically. And you try to build and train your neural network. Third thing you will do visualize loss and accuracy. And then at the end, you will do regularization and for this. So this part, regularization, loss, accuracy, building the network and training, all these things you have learned in your earlier class. That's what I followed. So this is the exercise you will do. So I just commented all these things because we'll do step by step. Okay, secondly, you did this part, you do another part. You download this data set, which is this house price data.csv. This you will get here in this yes, this download data set. You download that one in your computer. This is small data, and then push it in your folder. Push it in your Dropbox folder. Not Dropbox folder. Push it in your this net Colab folder where this file is here. Okay, if it is done, then you can try to run one step by step, and we'll go forward. Okay, so there are two methods. So this is the first method we are trying. We are downloading the data and use the data for our purpose. So here we are learning that part, and the next part of this code we will try use their data. Already that data is available, and we will directly use that data from the net. So this part, for this part, you will first import this drive with this Google Colab and try to run this. So you will do shift return. It will run that one, and you will ask for some permission. So this will first line load, and driver helper will be loaded, and it will be started mounting, and it would ask for authorization. You give the permission. Once you give that permission, it will be mounted. Okay, so for my case, it was mounted already. I hope some of you already done it. Okay, so you can see your folder in this Colab netbook. So you have to correctly write that path here. Maybe last part of this path. So if you correctly write it, it will give you the content. Okay. So you can give or change the directory of your project folder. Here I kept it same. Then in the next part, you import pandas, and now you are accessing the data, that CSV file, which is already in your folder. You are accessing that one. Okay. Okay. Now, if you try to see the type of this file, this DF, it will say it is a data frame. So it is a pandas core frame, data frame. It is telling, and it also defined that how you can include that one. So you can go through that one, that what are the type of data and all these things. So now, if you run this one, df.head, so it gives the header, first 5 lines of the data in a particular format. It is a very nicely organized way, which is available through this pandas framework, where you will see that all the columns have a have a name which is actually defined here. You see these input feature vectors are defined here. So this is the lot area in square foot. This is the first entry, then overall quality. So this is a housing price. So now you try to understand the problem. So you have this is the from 1 to 10 attributes are there. 10 features are there basically. So among the feature of this housing, this area, quality, overall condition, then basement area. So this is European probably data. So there are few entries like fireplace, those are there, garage area, and also number of rooms above ground, number of bathroom, number of full bathroom, half bathroom, and total basement area. So these are the 10 features you see here written. And finally, so these are the 10 features. And here, last column is that above median price or not. So basically, it is asking whether so you know median basically. So this is the halfway of this full distribution, either ascending or descending if you put it. So whether it is above median or not. So it is a, now you understand that this problem is the binary classification basically. You have a answer 0 or 1. If it is above, it is 1, and if it is below, it is 0. So this 0, 1, 2, 3, 4 is the how many data points you have. So now if you run this shape, so I run this one with head. Now next, if you want to see the shape of this data file, it is 1460 data files are there. So basically, you have so many informations for each of these X value and Y value. And you have total 11 quantities. So you can write down these quantities here. And you see that those earlier we discussed this one. Area, quality, condition, all these things are there. And finally, this is median price is there. And this data type is object here. So as we told that once we have this data file, this is a simple data file. Now we have to do some kind of pre-processing. Now, if you go to this that other link I shared earlier, so we have already went through the data, and these are the discussion we have done. So this is the data set. So now to convert our, so we don't, so this is a very user friendly way, but finally what we need is the data to convert, which is the way machine learning programs can be useful. It is useful in the in our course. So we convert our data frame into some arrays, and we just store the value of this values of this DF, and that data set is now available to us. So if we look at this data set, it is those quantities we have gone through here. So only those data, total 11 entries basically, and you have 1460 data point. So now you have to break this data into two classes. One is that all the row of the data set of first 10 columns, which we call X, and last column, 11 column, we'll call Y. So you can access those data set this way, where all the rows you will take here, and you take the first 10 entries or first 10 columns as X and Y. So if you take these two, you can try to see that what is the first entry for X. Similarly, you can try to see what is the entry of Y. You will see that X has the first 10 entry and Y is the last number. Okay, so I hope this is much easier and this data you understood quite okay. So now we'll go to the next step. So although this data looks complete for our purpose, so this data is a complete attributes of what is useful or input data for our machine learning purpose. But as such, this data is not useful in this present form. So we have to do some kind of pre-processing. So normally in the machine learning, there are significant amount of discussions going on in the pre-processing stage. So some part of the pre-processing is that if your data is incomplete, for example, you are actually using some kind of real data. Say, for example, you want to predict the election, and you have taken the public opinion, and there you have taken defined quantities asking for the public. So some of the numbers probably, or some of the features will be absent probably. Some of these things I don't know, those kind of answers will be there. Similarly, you may have to think about that whether all data is or all features are reliable or not. Many of the cases of the real data, many of the data are not reliable. Say, for example, some of these questions you are asking for the elections or pre-election, then many people are telling what they thought suitable at that point. It may not be the actual answer. So, but point is that your final analysis depends on all these data. So you have to very carefully look at the data and understand the data structure and implication of this data. So based on that, you have to see that how you can handle those data. Here it is very simple because there is no incomplete data, as well as, so this is a real data. So here we believe that all the entries are correct. But at this present form, it is not useful, mostly because, say, if you look at this first column, it runs in the order of thousands, so few thousand basically, whereas many of these other entries are between 0 and 1, 2, and some of these entries order of 100. So they are not properly placed in the standardized format in these features. So what we have to do, the scaling of these features so that they can identify, or they can they can be realized in the machine learning framework in the same weightage, at the same weightage. So to do that, there is a feature called pre-processing. So if you run that one and you do this min max scalar, so by doing that one, you are doing the scaling of each of these quantity between 0 and 1. So that's what you are doing. You will run it, and then you will say, okay. So now if you see this scaled form of X, it is scaled form of X, which is now very small numbers. All of this has changed now. All of these numbers have changed to very small number between 0 and 1. So now you see that so it was converted or scaled up to into a small number between 0 and 1. So this is full X scale. Your Y remains same between 0 and 1, either of this binary classification. Now in the next level, you have to split the data. So what you have to,
Hello.
yes,
Sir, can I ask a question?
yes.
Let's say if we don't do this uh, normalization, which you are doing for the features, and then if we train the model, then is it like for this reason that we have not done the normalization? Can it be that for, let's say, for the zero level where what we are doing, there is two levels, 0 and 1. For zero level the scores are like much more difference from the score of the level 1. Is it can be the reason for it?
I could not follow. Score of the
No, no. So what I am trying to say that let's say my score will always be like from 0 to 1, but that can be that one thing for one, let's say one house features, the score is like, let's say 10 to the power -6, and one score that is 0.99. So that is very much sparse, right? So what I am trying to say that this thing, can it be that this thing can happen only we don't do the normalization?
correctly. So basically, if you don't normalize, so you can very easily try to visualize it in two axes. Say you have a one feature x1 and one feature x2. In x1, these features are kind of extended up to say 10,000, and where x2 is very small. So ultimately, what you are trying to do that in your this space, two-dimensional space, ultimately this problem means normally all the machine learning problem is that you are trying to represent your data in a multi-dimensional space. So in the multi-dimensional space, even in a two-dimensional space, you can realize that if it is data is very sparse in one direction and other direction it is very condensed. So ultimately, you have to look at the data. You have to find the decision boundary. So that's what you learned in the previous class. You have say two class of data, and some way they are separated. And what you are trying to see is some kind of decision boundary between them. So if it is a if the data structure is such that one side or one variable is very sparse and other one is very condensed, so basically you will choose a basically decision boundary which will be which won't be very good in that directions. So that's why it does not work if it is not properly normalized, at least in the same scale. Means it need not to be 0 and 1, but at least in the same scale you have to keep. So you can try this same exercise what you are telling that with this original data, you will see that it will be very poorly, means after execute, you will see that it will be very poorly represented. So this is one part of the pre-processing. So pre-processing is not the only one pre-processing. This is the very basic pre-processing, I would say. And normally in our physics problem, your pre-processing depends on the problem itself, or many a time what are the underlying symmetry and what are the data structure. Many inputs can go in your pre-processing state, and pre-processing is extremely important. If you don't correctly choose your pre-processing step, ultimately you won't get anything out of this data. So basically, that's why pre-processing means, unlike, although they are, as I told, that unlike particle physics or this our area of scientific research, our data is mostly pure. Whatever the data, experimental data we are taking or simulated data, our data are mostly pure and trustworthy. Even then, you need a significant amount of pre-processing. And if you talk with the people or machine learning experts who are doing a real life analysis, then you will see that completely they will spend their most of the time, almost 60 or 70% time only in the pre-processing basically. As I was telling that there are many gaps, many wrong attributes of the data. So they spend much more time on that space basically. We are lucky that we don't need to spend that much time in the pre-processing, but our things is more complicated in another aspect because our data is more complex, more abstract, I would say. Because here it has a physical meaning. Sometimes, some way you can realize that how you can handle that one. And many of our research data or the way we use is a abstract data. There you have to somehow formulate that which is the best pre-processing step so that it can be realized in this machine learning language. So when you go through more problems or more kind of actual problem people are working, then you will learn many of these aspects. So here we gave example of a very simple one, just a normalization or standardization of each of these numbers. And so now let's go to the next step. So here we have a full data with this 1460 data. So we have to split that data for training, validation, and testing, these three. So here you can follow that one, that we want to make 70% data to train the model, then we want to validate, and then 15% data we test. So we split that data in two steps. So remember, we have to split both X and Y. So first we split the full data into a set of train and another set of these two. So training is the 70% and validation plus testing is 30%. You can do it this way, where you have test size, you are telling that 0.3, and next stage you are breaking this total 30% into two parts. One you call validation and another is test. So finally you will get the full data splitted in this class. Okay, so you see that 1022, these are the training sample, 219 and 219 are test and validation sample, and these are the Y Y values are also splitted in the same way. So now we have to build our architecture. So this is a simple architecture where we have a input layer. So as we have discussed, we have a 10. We had 10 input data, features. These are the 10 input features. So this input layer must have a 10 block here. Its size is 10. Similarly, you have a 2 hidden layer, and each has a size 32. And finally, one output layer with size 1, which will give you some prediction or number between 0 and 1. If it is close to 0, you will conclude about this last number. Whether median price is above the median price or below the median price. So basically, that number is predicted by one output layer. And similarly, another point you will see that each point is connected with all these points. So it is called fully connected, as you have learned already. Okay. Third thing is that, so this is input layer and output layer. 2 hidden layers are there. And these are the 32 neurons you are using. And your activation, you already went through activation, I think, in the last lectures. So Yes. So basically, we'll try to see that how it is working with these two kind of activations. The first and second hidden layers are with this ReLU activations, and my final output is with this sigmoid activation. And okay, so another thing we have to learn. So here we are choosing a model. There are two terms. One is sequential, one is dense. So dense means basically all points are connected with in the next layer. So basically it is a completely fully connected. So that's why it is a dense layer. And sequential means that when you are building your model, you will building one stage at a time, like these three dense network you are choosing. So it is building one upon another. So it is sequentially you are building. So, so as you have, I think let me see. Here you went through this activation function in this last lecture. So it was talked about this ReLU, which is very simple, which is one of the most simple and mostly widely used activation function. Where is the another one is sigmoid. Sigmoid is this one, this red color, which is if you go negative side away from x, it is 0, and positive side away from x, it is 1. Basically, it is between 0 and 1. So, what are the features of these two activation functions? So, as you already know, these activation functions are very intrinsic part of this neural network, or an important part of the neural network to build the non-linearity. That you know, all of you, it is a very important concept, and it introduced this non-linearity. So only one problem with this sigmoid is that few problems are there. Sigmoid is a very nice function in a sense that it is between 0 and 1, and it some way connected with this probability basically. So if you have two class, there are you have to attribute some kind of probability with each of this class. So between 0 and 1, it is varying. So it will connect with this probability. That's why at the last stage, or at this final layer, we have used this sigmoid function. On the other hand, ReLU is a very simple function where it is above x is above 0, then it is a just function of x, and the way it is constructed, its derivative is very simple, and it takes much less time. So it is that's what it was told, that it is widely used because it is a very fast and effective one. Whereas sigmoid has the advantage of this binary classification, but it is a very slow function. To calculate it is computational power is too much. So these are the steps you are taking. So if you look at this website, yes. So it is, let us run this one. And second part, what we are doing, we are choosing this algorithm for optimization, which is gradient descent. You have gone through that one, I think, last class. here it was discussed. So if you can follow that one, otherwise look at that class note also. So here, gradient descent was discussed, then atom optimizer, and also, yes, it was discussed. So basically overtraining was also somewhere it should be discussed, and mini batch also discussed. Okay, so we will try to do that. So our loss function is binary cross entropy, which looks like so 1 minute hold for a minute. Sorry. I hope all of you could run this one. And third entry is the accuracy. This is the another metric we want to try to verify. And so once you set your model, now it is we are ready to train our model. So to train our model, we are giving this training data for X and Y class, and we are running in a small batch size of 32 and epoch of 100. So it was discussed, that's what I followed here. It was mini batch, and it was discussed how it was done. So you follow this your theoretical notes so that you can understand that one, and correspondingly you can fully realize that how it is calculating your loss function as well as accuracy. So if you run it, you will see that already it is generating data for each epoch. And one thing you have to follow, that your loss has actually started from some value, and gradually it is decreasing this loss, whereas your accuracy is increasing. So this is the training loss and training accuracy, whereas that validation loss and validation accuracy is also printed here. So it takes some time. After that, you will see that finally whatever your training loss and accuracy is here, and whereas your validation loss and accuracy are even here in that final epoch. So after the aggregate, your final evaluation of this test sample you can do. So basically, you have to notice a few things here. One is that, okay, we'll plot it afterwards, basically, more diagram wise you will look at it. But here you notice that this loss function decrease up to 0.27, whereas this validation loss is actually decreased much more, slightly more, 0.31, whereas accuracy is 0.88 or 89, and it is almost similar here, 0.88 and 58. So your validation gives a very good representation of your loss function or accuracy in your training also. So if you also try, so basically it represents that your validation of this model is quite okay. That is also represented here. So if you draw this this one with each epoch, how your loss is evolving for the training sample and validation, you will see that it goes up to say 0.3 or 0.27, this number. For validation, it stops before that one. But this gap is not that large presently. So you already, this point was already discussed with you for the overtraining of your data. So I hope you understand that why it is happening and what is the danger in it.
Hello.
Yes.
So here we can see that there is some gap. So isn't it
Yeah,
some
we'll
harmful?
discuss more on this one. So I just left it open so that we'll go further on this.
Oh, okay, okay. Like, okay.
Yeah. So
And one more
here,
thing I want to ask,
yeah,
that sometimes that curve we are getting smooth, right, to both the curve, but sometimes it can happen that it is not smooth. It is something somewhat like there is some fluctuations in the curve, right? So, can you tell that what can be the reason for the fluctuation? Let's say for only training loss, there is if I get some fluctuation
yes.
with epoch, then what can be the reason?
One reason can be, so it mainly depends that, so each epoch you are basically accessing small class of your data and you are, so you know this gradient descent. You are trying to look at the gradient and you are trying to find the which way you have to go for the minimum. Okay. And if you take the full data sample and try to find that what is the gradient of that one. So as you are seeing that you have a huge amount of data and you try to find the full data, what are the and you have a multiple attributes, and you are telling it is a multidimensional, basically multidimensional problem where you are trying to find what are the local or global minima. And to do that one, when you start with the full data, it is a very kind of computationally impossible almost. So what you are trying to do that you are in every step you are taking a batch, or in every epoch you are trying to take a mini batch of that full data set and try to find some kind of proxy. You can tell the proxy of that gradient, and that way you are trying to find that how we will find that gradient of this slope. So that was here it was discussed. For example, if you see that because you are many randomly choosing which set of data you are looking, and so basically each time it is not the perfect, sorry, it is not the perfectly you are going towards the minima, rather you are actually somewhat changing the direction many times, and but still you are getting going towards the local minima. That way you are trying to get back into that line. So that structure of this one attributed because of that one, that how correctly you are following that curve. So whenever you are in each epoch, you are actually doing some away from this along the line of minima, then it will actually increase the loss, increase or decrease the loss. So this fluctuation is happening because of that one. So you can choose your, so for example, when you are looking at this batch size and epoch, here this fine balance is there. So if you take this too small batch size, for example, then say for example, if you look at each data at a time, so then whatever the gradient you are calculating from that small sample, 1 or 2, then it is mostly faulty. then you will get a more kind of jerky journey rather than if you have a larger batch size. But if you increase the batch size, then it is actually doing a much more complicated calculation. So it is a fine balance. So here, say for example, you have a total numbers of data is order of 2000, but you have a small size batch size of 32. So which correctly calculate this proxy for this loss function, and which correctly, that's why you are getting mostly correct one. But if you change those variables, you can get a very means jerky journey basically. Similarly, if you look at this accuracy, here you will see the accuracy, this another function. Here you have a at around 86 or 87% of accuracy. But mostly you see that both training and validations are going hands in hand. So they are very reliable in that sense. Now we'll go to the next stage where till now we set our model, one model. So we'll very quickly we'll go to the model 2. Model 2, what is the very similar model like model 1. Only you will see some small difference. Like it is a more complicated model. You have increased that dense network, another 2 hidden layer you have included, and you have nodes around 1000. So it is you are constructing more kind of complicated model here. Okay. Another, yeah, these are ReLU and sigmoid. Another thing you know, this another difference is this optimizer. Here, Adam optimizer is taken. So compared to this gradient descent, I think Adam optimizer is also discussed in your class earlier.
Yes, sir. Yes, sir, it is discussed.
It is done? Yeah. So only difference here is that apart from the normal gradient descent, you include some kind of momentum. So basically, you trying to find the local minima where earlier you were looking each step and you are jumping each step and trying to going towards the minima. Now you are trying to see the momenta so that if there are very high momenta, so you will jump the step. So rather than a small step, you jump the initial step. When momenta is low, your step size is small. Where momenta is too large in certain direction, you make your step size large. Basically, this is the concept. So such that you can very quickly reach your reach your lowest part of your loss function. So this is very useful in that sense. So these are the 2 difference from the earlier code. One is that your network is more complicated with a more number of nodes, and also you use this Adam optimizer, which is very fast, and it runs try to find a minima very fast. Now, if you run this one, if you formulate your model and you run this one, you will see a very interesting structure. You see, your loss function already starts from a very low, already 48%, and it is going to 25 in the 4-5 step. And your accuracy also from starting from 77%, it is almost 90% in 6 or 7 step. So if you compare with your earlier model, it is converging very fast actually, and it is also very fast. Means it is running also very fast compared to the earlier one. So last time we have got lost around 28. We have crossed that one long ago. It's still improving. So second thing you observe that discrepancy between your training and validation. So although you are improving in the training part, your validation does not agree with that loss or accuracy. That is the important part you have to notice here. So now we have to ask that question, which is the better model, the model 1 or model 2? So although model 2 has a very low loss function or very high accuracy, but it does not agree with this your validation data. So why it is happening? So you went through that one. So
I
anybody
I
can
think,
answer?
sir, it is for overfitting because the
Yes,
model has.
Swam. I think that you answered many of these things, but today's class mostly I was trying to see that what is the preparedness of many others. So you will answer, but let others also try to answer, because means I am not getting that feedback whether others are also understanding or kind of connect this with these previous lectures. Anybody apart from Subham? Open up.
Hello, hello.
Yes.
So I'm thinking that model 1 is better than model 2
A bit
since it
loud.
is not.
A bit loud.
So I'm thinking, hello.
Bolo.
So I'm thinking that model 1 is better than model 2 since in case of model 2 it is not working so good in validation sets. So
Yes.
it will be useful to use model 1.
Okay, very good. But can you try to see that why model 2 is not very good? Means why model 2 is behaving this way?
So what I'm thinking is that it is learning very good in case of training sets of data, but so it is kind of overfitting, means overly learning these things in training sets of data. So simply this is the I think overfitting problem,
Yes,
overtraining problem.
this is overfitting problem. ठीक है. So what actually happens in the overfitting? So anyone else can you tell that when someone is telling that it is overfitting, what actually is happening? Anybody? So okay, so earlier we were telling that you have a two class of data. So your multidimensional space, you have a, so all the data are distributed, and what you are trying to find a decision boundary between these two class. Only problem is that you have a, your dimension is too large, dimensional space is too large, and now in this space you are trying to find that decision boundary, and your model basically try to help you or train using this training sample what are the decision boundary. So to find that boundary, what you are trying to find that what separates these two class, one class from the another. You are not trying to find the local distribution within this class. So what happens that so in this multi-feature dimension, whatever the relevant feature which differentiate between two class, you better you understand or better you find out, that will give you the better model. But at some point, if you are going trying too hard, then you are trying to find a local feature of this one sample. And local feature means you are actually trying to fit the data too literally rather than its feature. So when you are doing that one, probably your sample set, the training sample set, will work for that one. For that class, you are actually putting a decision boundary for the each point, and you are actually covering each point, and you are very nicely separating these two classes. But whenever you are throwing the new balls in this space or new data in this space, they need not to follow that same feature or same kind of distribution. So they try to deviate from that one. So that is the kind of understanding you can develop basically. So because of our very complex model we have created, and most importantly this atom optimizer we have used, which jumps to find the minimum of this loss function. And to do that one, very easily try to find that decision boundary, but it tried too hard to make it more relevant for the training data, but not for the other data. So this is not the reliable model in that sense. So your prediction power has lost basically, although you have a very good accuracy or loss. You cannot use that one for the any other data set or any other validation or test data set. So basically it is not useful at all. So how can you improve that one? So you want to use the same model 2 kind of scenario, but you want to improve with this separate level of improvement. So here there are few methods of regularization. This is also taught in your last class, which is one is L2 regularization, another is dropouts. There are few classes of them. So we'll try to discuss that how it is working. So if you want, I think it is taught. here. So here it was got. So you can go back to your lecture note and try to find that what are the possible regularization you can use. So you see that one way of regularization use this kind of lambda hyperparameter with this addition of another weight function. So with your usual loss function. So you redefine that one, and there are few ways to do that one. So here it is defined with a lambda parameter with this W square, where W is the sum of all weights. So this is L2 regularization because it is square, it is not linear. This is called L2 regularization, and it is most commonly used. So what is happening? So physically you can understand this way. So in this space, you have some kind of signal data and background data side by side. And when it is overtraining, what it is trying to see, rather than it try to find the decision boundary, it is try to find a decision based on this only signal point. So if you have a signal point here, another is here, it try to find a boundary like that. Rather than you need some kind of based on its property, rather than that, it try to find too low in each point, basically. Now you try to realize that how this in the neural network, how they find this kind of non-linear description of this region boundary. So basically, that depends on each of these weights. So unfortunately, it is better described by pen and paper or board, but I am feeling difficulty that how you represent that one. So basically, when you try to make a too much overfitting, one of your weights has to be too large. One or two weights has to be too large, so that it satisfies some small space with a very distinct signature. So if that happens, then you are generating some kind of punishment for this large weightage. Here you are generating that kind of punishment. You have a large weightage, it should be punished. So it is a it is exactly this concept is used in this class of regularization. I don't know whether this other kind of regularization you use, like dropout method. This is another very convenient method. So in your earlier, we have seen that each point was connected with all other points in the layer. So if you can randomly drop some of these points. So here I tried to write some of your points, and I tried to add some reference so that you can go through and you can try to realize that one. So as I told that L2 regularization control overfitting by penalizing extremely large parameters, whereas dropout works because it randomly excludes some of these neurons. So a priori, it does not know which part of this nodes will be absent. So it does not rely on each of the neuron, rather gross property of all neurons. So that's why it does not overfit that data space. So these are the two classes. So if you go through these links, probably you will have a better understanding. And also that earlier notes where it was taught. Now, along with this earlier model 2, it was added for this these two kind of regularization. One is this L2 and another is dropout. It was given. So now try to see that all others are random optimizer and all others are same. So only thing is that it was included along with this regularization with L2 and subdrop. Now you try to realize that how it is working.
What about
Yes.
the problem?
I cannot hear you.
Sir, hello.
Yes,
Sir, why the loss is so high in this third model initially?
oh, you already started running. Okay, let me start. I don't know why it is very large at the initial phase. I don't know. Dipanshu, do you have idea?
No, sir. I think that just might be because of this random initialization.
So it is still very fast. So we have to see what happening. So it is very fast, but still you see that now training loss and validation loss are very consistent. These are very consistent. How low you went there last time? This is 0.11 and 95%. Okay. Whereas
Right. I think, sir, that is just because of that. Because since we have added this L2 regularization and the weights are initialized randomly, so the lost in first epoch adds for those value. And since those weights can be different than zero, so that's why.
okay, so you are telling that because of the addition of regularization, initially that was too
Yeah,
large.
since the weights are not optimal in the first epoch
Yeah.
itself.
It will be same for dropouts also, right? Because that also
Yeah.
randomly take the weight zero.
That randomly choose some 30%. What is the number? 30% or something we do. Dropout is how much? 0.3. So 30% of nodes were dropped randomly. Okay. So final accuracy is 88%, whereas last time actually validation accuracy was almost similar, 88%. but training accuracy was very high, 95%. What happens in the first model? This is model 1. That is also 88%. So 88.9% it was. Now, so now this model is very reliable. If you try to plot these two, both accuracy and plus is better.
Hello, sir. Hello.
Yes.
Should we be bothered with these fluctuations? Like there is some fluctuation with both the accuracy and.
A bit loud. Somehow my
So what I'm trying to say that should we be bothered about the fluctuation or the loss, like the fluctuation in the loss curve and the this accuracy curve?
no, but it was stabilized. Yeah, although it is fluctuations are there, that your finally it was stabilized. You will see that these numbers are very consistent. Or this number, okay, so your validation accuracy has some level of fluctuation, 85, 84, again 89, 94. Probably you have to tune your model properly so that you can reduce your fluctuation. So that level of work has not done, but if you see that initial model is very quite okay, very robust.
Tuning means here like the batch size and other things we need to change.
Yes, model parameters you have to calibrate. Okay, so I hope that this program helped you to understand that what you went through that one, this earlier lectures. So now let us move almost 1 hour, more than 1 hour. We are talking about this model very slowly. Each step we have seen. Now we'll move to the another model. So are you okay to go to the next model? So what is the status of everybody? Nobody is talking. I don't know. And it is the problem with this online thing. I cannot see. Okay, since nobody is complaining, I hope that everybody could run it. No, running it is okay. Means basically it is not a problem to run it because I already checked it is running, so it will run. But the point is that whether each step you are understanding and kind of gathering information from the earlier lectures. So that is the most important part. Okay, let's move to the another one. This is also the same way I am putting it. It is a CNN model. So I am sharing this. So now try to open and save it in your Google Colab, and also open this website, first website, where it is described how we will run it. Step by step it is described. So let us try to see that how it is working. So CNN was covered. Here. Oh, this is the dropout was discussed, yes. So everybody opened it? So you will learn these three stages here: exploring and processing this data. This is different kind of data, unlike the previous very simple raw data. Here it is a image data basically. And second is building and training our convolutional neural network and testing with our own image. So here we will do slightly differently. This is the data set, particular data set, which is already here I listed that it is a built-in data set in the Keras. So if you look at this link, you will see that these are the different data set already there as a built-in. Also, for TensorFlow data sets are also available. So we'll try to see this small data set in this one. So try to understand what are the feature of this data set. So it is a very tiny image. Each of this image is very tiny, only 32 by 32 pixels. So these are the image. Say for example, this is level with this 10 class, 10 possible levels: airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. These are the 10 class. For each class, there are multiple images. So data set total size is this 60,000 image, and where we will try to split into 50,000 for training and 10,000 for testing. Okay. So if you see this, because 32 by 32 pixel, it is very small. If you make it bigger, it will break. So it is very difficult to recognize that one. But once it is very small, you can recognize these are birds, these are automobiles or cats, you can recognize. So to start with this data, so we'll directly accessing that data without saving that one. So first step is this one. We'll take that data, import that data, and we'll save for training and testing. So it will download, it will take some time to download. It depends on the speed of your network. Okay. So once you loaded this data, then you can see that so you print this X train shape of this training sample, which is that 50,000 data with 32 cross 32 and three another direction, which is red, green, blue. It is a color pixels with red, green, blue. So this data looks like this one. Now, in the you can plot some of this data. For example, this first image, X-train 0, the same data file. If you these numbers are RGB values, so you won't realize anything from this data. But if you try to plot in Matplotlib, then you can try to see this what it is there. But since it is very big, it is means 32 cross 32. You can see this pixel size 32. Each pixel is this big down here. So it is very difficult to understand what it is. But if you make it smaller, you can see it is a training class, which is at level 0, level 6, which is frog, basically. Okay. Similarly, you can take the next one and this is class 9, which is truck. Yes. So I don't know whether this already you have done some amount of CNN, no? Now it is not a binary class. You have a multi-class. You have a total 10 class are there. So it is now not possible to do the same way we have done the binary class between 0 and 1. So earlier what you have done, that you have finally got the one neuron which predicts some number between 0 and 1. If it is close to 1, you are telling it is 1, and if it is close to 0, you are choosing 0. So that way you are predicting which way you are doing. Now you can no more do that one between since it is between 0 to 9. Now now you have to do a trick. Basically, this is a that trick is one hot encoding is this trick, where you will write an array of these 10 classes, and for each class you will put only one. Say for the first class you will put 1 in the first one, but all others are 0. Similarly, second number is 1, all others 0. So that way, this is called one hot encoding. This way, if you define your all the classes, then it is very easy to describe all the classes in the multi-class classification. This is a multi-class classification problem. So now all your Y-train data, whatever your this number was there, level was there, you have to convert into this kind of one hot encoding thing. So you convert from your category to this encoding format. So once you convert this one, say first one, which was earlier this automobile or truck was there, it was number 9. And now you will see that it is converted into this one hot level, where it is all 0 except this last one, 10, 10, 10, 1. So once you converted your X values, these are your X values, basically, your input sample data, and your Y value is now in this format. Now, second step, your pixel values are, as we discussed, this RGB values are running between 0 and 125. Sorry, 255. So you divide it 225, then all the numbers will be modified between 0 and 1. So all these numbers earlier you have seen for one image in RGB format was between 0 and 225. Now this is converted to something like this one. You try to see this first data file, which was from, and this become all between 0 and 1 now. Now you build your network. So build your network means here you already gone through that one, this how this network works for this convolution. So now each pixel has some number. each pixel has a number, and also you create some kind of filter. This is 6x6 image. Also, it was, yes. So now you have a different filter. This is 3x3 filter and multiple copy of filter you take. And you run this filter over this image and shift it one by one. And that will create you this convolutional of this multiplication of this matrix. And from that, you will get one number. And that way, this is very interesting because unlike the previous way. So basically, now you compare how this your deep neural network was working. You have a input data and your hidden layer where you are trying to connect with some kind of weight and biases, W and B. Here, in terms of that, you are actually sharing some kind of same number for throughout the whole image rather than the earlier case. So this weight sharing has a deep utility, and it also simplifies your problem. So because your this computation of this problem become much easier and much simplified. Also, because of this sharing of this weight, creates some kind of symmetry. They can be realized here. For example, when you are looking at this image data, you don't want to just rely on the position of that image. Like frog is somewhere in the left corner or right corner, you should try to recognize as a frog. Or if it is somewhat tilted, even then you try to recognize as a frog. So you try to mimic something somewhere so that you can realize that property of this translational or rotational invariance. So these features are very useful. Here, by sharing weights, it actually creates somewhat invariance in these translational properties. So here, in this example, it was shown that how this new matrix was created. So another concept is here, zero padding. So to use this image, you actually padded this one with zeros around that, so that when you run with your filter, you can access all of your points. So this was described here when you are running this your filter. So now this filter, you can move either one step or two steps. That way you can. So this is the formula. So if you have this n cross, ours is 32 cross 32 pixel image, and if you create some filter 5 cross 5, and you shift your filter by S unit, and also you use the P, this is the output you can create. So you can think about it, and you will see that this is the size of your output. So this problem for us is very similar. We have a RGB 3 layer of data, and each layer we have a 32 cross 32, and for 3 layer, and we'll construct some kind of filter, and we'll run over that one, and to create this this next level of data. Sorry. So so that way this sequential model was created. So here you see that your 32 . So your input shape was 32 cross 32 cross 3 with padding, and your activation function is ReLU, and you are doing convolve with 3 cross 3 filter with number of 32 number filters. So in the first step, you are doing that one. In the next step, you don't need to give the input shape because it will automatically take from the previous step that what is the shape of the next level of input. And then once again, you will do this padding, activation, and convolve with this 3 cross 3 filters. Then next level, you do this max pooling. For this pool size of 2 cross 2, you take that maximum number from that pool, and also you do a dropout in this level. So after doing these 3-4 steps, you have a much smaller data actually. Then you will do once again this convolve, and second time convolve, and finally you will do this max pooling and dropout once again. Finally, once you get that data, you flatten that data as a normal neural network kind of flatten the data, and then with this dense structure, you do this add layers for this dense layer with this ReLU activation function, and also dropout of 50%. And finally, you are using this softmax, which will choose between this among these 10 classes. So I hope these all steps were understandable with you, because these exactly same steps were discussed here. So I chose this problem because all these steps were done here. You choose your filter, you run your filter for red, green, blue, each of them. And for the multiple filter, you create that thing. So yes. So this is the pooling and then fully connected layer you are creating. Max pooling in steps here. And after flattening, you have this kind of data. And then you have a dense layer where you are trying to get the output. Yeah. So exactly same thing we are following. Only ours is slightly more, several more layer of convolution, 2-3 more layers of convolution and pooling. Otherwise, this is the exactly similar structure. So it is instructive. I would say that look closely what are the activation shapes, size, and also number of parameters. You try to calculate. It automatically calculates in your neural the way it is constructed, but it is instructive if you try to calculate your number of parameters and how it is going, and you will see that even though this is kind of problems where it looks like a huge number of parameters, but because of the sharing of parameters, the total number is not that large actually. So this is a basic advantage here. So let us now see that if you run and the same thing. Yes, it gives a summary, which is similar thing what you have seen this lecture note, where each layer was discussed and number of parameters calculated for you, and you can by hand you can calculate and try to see that whether it is consistent, why it is happening. It is instructive to do that. So total number of parameters and trainable parameters are listed here. So here similarly loss, optimizers and metrics were used like last time. Now, once again, you have a batch size of 32 and epoch 20, and you split for the validation for 20% of data. So it is a much slower than the earlier. Now you realize that it takes quite a long time. I think it will take ages, but hope everybody can run it. The best part of this Google Colab running that it is not running in your machine, so it does not matter whether your machine is very slow or not. It will take quite long time. So yeah, let it run because yeah, let's see that how long. It seems that it is quite slow actually. It will take quite a lot of time. By that time, if we want to discuss something, we can discuss. Probably that is best thing to do. So if you have any question, this is that right time. We can discuss on those points.
Sir, can you hear me?
Yes.
Sir, is it possible to calculate the hyperparameter lambda to know the exact value?
Lambda where?
The hyperparameter.
In the regularization?
Hello?
Hello, in the regularization you are telling?
Yes, sir. Yes.
Yes, you have to try with few different. So basically, that lambda is a tuning basically between. So lambda is tuning that how significantly you will punish based on its weight parameter. No, that's what I told. That if you have a larger weight, you punish that thing, and you are telling that it should less contribute in your loss function. So that larger weight should not contribute there. So weights are, so now if you take very large lambda, so then it will try to squeeze that very small values of weights, but some flexibility of weights are needed to realize that your local minimum. So if you give a very large value of lambda, then it will stay somewhere in a very shallow local minima. Means it won't find actual minima. It will try to stick with a local minima, which is much larger actually. So what you will find, it is under trend, or your result will be accuracy will be very low. So on the other hand, if you take very small lambda, then it will keep on taking a large value of weights, and this problem will stay. So you have to balance between them, and you can play with your these numbers, where it will give the optimum value so that your samples between this validation is giving the close to. So basically, it will gradually going close towards your training sample, and once it is within this reasonable, say within 5% band or something like that, then you will stop there at that point. If you try to go beyond that, probably you will lose in your means you will undertrain your sample here. So you have to parameterize it that way. You have to compare and parameterize.
Okay, sir. Thank you.
So as you see that it is still second epoch it is running. So I hope that it is taking around 5 minutes for each epoch. So it is hopeless. It does not seem that it will 20 epoch means it will take 1 hour. So you have to let it run and it will carry on. But here, since these plots are there, you can see that from my earlier run, these plots are there. It is not very good actually training and validation comparison. So you see that there are certain amount of actually tuning is needed. This is not very nicely calculated for the test sample. But test accuracy it is giving 76%, which is still poor. So now, in this next step, one can save this trend sample, and this trend sample can be used for this your own image. So you don't take one of this image from this one. You can actually bring some of your own image, own sample image, like it was shown with this cat, and you can try to see whether this is working with this model. So what you will see that it will, so as I was telling that because of the softmax, ultimately it is giving some kind of probabilistic value for this all 10 class. So probably that was discussed here. Softmax was discussed here. Yes. Right. So here this is the way you activate. So for this 10 class, it will give some kind of probabilistic number this way, so that total sum of this probability will be 1. So your each of this class will take this kind of value. So you can say that from the model try to predict, and it gives the highest weightage for the one class. Probably for the cat it will give this kind of 0.84. For the other class it will be a very small number, but certain probability will be there. But when you have it has a confusion among the multiple class. Like for example, you will see in your this model that many a times there are confusion between, say, for example, some of this automobile with this truck. Some of this automobile look like a truck, so then it may have confusion, and then you will see that almost these two takes the around 50% or 48% of these two value, and rest of them are close to 0. So you can try it there, and similar thing you can use it for the other class of problem also. Similarly, here we listed many different class. You can, for example, use this MNIST class. Sorry. This one class probably there was a tutorial yesterday by Ritesh. Can you remember that?
Yes, sir.
So this is handwritten 0 to 9 basically. You have that class of data, and you can recognize among these 10 classes. Similarly, MNIST data is also there for fashion, means there are all those fashion items, they have a data set. This California housing is similar data set as you have seen this earlier. You have done, you saved that data, but you can try to do this, use this data, and you can do the same analysis with this built-in data set. So these are the very useful data set where you can directly use your code, and you can try several. For example, this is this movie review sentiment classification. So from the different words in the movie review, it does the sentiment analysis and classify whether the movie is reviewed as a good movie or bad movie. That way, sentiment analysis you can try. So there are many interesting problems you can construct without even saving the data. You can try to some of these models, and also you test your model with this data. So another thing is that, so here after doing that one, so it gives some kind of probabilistic input, and with this certain class basically. So it was listed. You will try that one, and many a times actually, apart from the first one, all of us there are very close to 0. So then it is kind of definitely predicted with a very high confidence. And as I told, some of the cases it may actually overlap. So then it is not very clear. Well, so this is still 4th epoch running. I think we don't need to wait for this full run. It will take 1 hour. So if you have any question, you can ask, and then otherwise we can stop this class today.